have a special guest, Dr. Frank Hill, who's from the National Solar Observatory and is the director of NSO's Integrated Synoptic Programme, or NISP, who's going to tell us what he knows about the importance of studying the sun in multiple wavelengths. Over to you, Frank.
So, hi, my name is Frank Hill. I'm a staff member of the National Solar Observatory, and I'm here today to tell you a little bit about the layers of the sun. I understand you had a little bit of introduction to that. And, as a quick review, the most visible layer is the photosphere. As you can see on the diagram, this is where the sunspots are located. It's where almost all of the energy, the heat, and the light comes from that keeps us nice and toasty warm here on the Earth. And it's by far the most visible part of the sun. During an eclipse, though, next year, you'll be able to see two more layers. One is called the chromosphere, and the other one is called the corona. So here are two pictures of eclipses. That shows you what you will see, approximately, not exactly like this, of course. On the left, you can see the corona. It's very faint. It's only visible during total eclipses because the moon blocks out all the bright light from the photosphere. And in this picture, you can see some streamers. You can see some location of some loops, and there'll be a complex. That's the most beautiful thing that you're going to be seeing during the eclipse. On the right, you can see a picture that shows you the chromosphere as this thin red colored rim right around the edge of the sun. You may be able to see bright spots, which are basically valleys on the moon. They're sometimes called Bailey's beads, and they may also be visible during the eclipse as well. So you might be asking yourself, just why is the chromosphere red? Well, why is it a different color? Well, there's a couple of things going on here. First of all, the different layers of the sun are all different temperatures. The photosphere has a temperature of about 10,000 degrees. The chromosphere is typically a little bit cooler than the photosphere at about 7,800. The corona is at a much higher temperature of 500,000 to 3.5 million degrees or so. There are even higher temperatures present during flares for very brief periods of time on the sun as well. In addition to the different layers being different temperatures, they're also made out of different stuff. So there's atoms from different elements like iron, sodium, calcium. You may be surprised at this, but there's all the elements up to uranium are actually present in the sun itself. So you have a combination of different temperatures at these different layers, and you have these different atoms in different amounts, and so you get a pattern of colors in the sunlight that can actually use to study the characteristics of the layers of the sun. And it turns out that the temperatures in the chromosphere, the most common element, hydrogen, produces a red light. So it's just the combination of that temperature and that atom being there that produces a red layer called the chromosphere. So this picture is a picture of what can be called the barcode of the sun. You go to the grocery store these days, or basically any store these days, and everything has a barcode of vertical bars of various thicknesses and spacings, which basically has the information of what that object is and various other things encoded in it. Well, this turns out the sun has the same thing. You can only see it when you take the spectrum of sunlight, which means you have to break all the white light into colors. You probably, when you were in school, you got a prism in sunlight and you were able to make all the colors of the rainbow. We have devices that can spread the colors out over a very long distance, and so we can see a lot of detail. This is called the solar spectrum, and this is a picture of what that looks like in the visible, that we can see with our human eye. And you can see there's a lot of dark lines, a lot of patches in there, little straight lines, sort of blurry patches here. And those lines are all caused by the presence of the stuff in the solar layers, the atoms of the various elements. The appearance of those lines, are they thick, are they thin, where are they, how dark are they? All that contains information about the characteristics of the layers of the sun in terms of temperature and many other things as well. So this is how we get all of our information about the sun, and indeed everything, all the stars in the sky have their own individual barcode, which will look different from the sun's because they're different stars. The colors in the sunlight are continuous in nature. There's trillions of them, so you cannot actually give them all names like red and blue and green. What we do instead, scientists give them a number, which we call a wavelength. And we can make pictures of the sun in very specific wavelengths or colors using our technology. So solar scientists can make pictures of the sun in very specific wavelengths or colors, and this even extends to colors we cannot see with our eyes, such as radio waves, X-rays, ultraviolet, infrared, and I will show you some examples of the sun in those colors later. We can choose that wavelength so that we can very precisely choose a layer in the solar atmosphere that can be studied. And if we make pictures in the different wavelengths, the different colors, you will see very different structures depending on the temperature of the selected layer. Here we have pictures from National Solar Observatory instruments of the photosphere and the chromosphere. Photosphere is on the left, and on the right is a picture of the chromosphere, and you can see these look very different, these pictures. You can see on the photosphere it's more or less flat except for the sunspots that you can see there, and the chromosphere shows you light bright areas as well as long thin elements that look like thread. Those are the filaments, actually. Those thread-like structures are the filaments. Anyway, those bright areas are usually around sunspots, as you can see by comparing the position of those bright areas with where the sunspots are in the photosphere. But you can see right there, you will now already have more information about the sun because you have these different looking pictures. So those are just two examples. The next picture shows 9 more examples. And these are all from a spacecraft, a NASA spacecraft called the Solar Dynamics Observatory. And they're all gaily colored, which is done by us. These are not the real colors that you see in the sun. We use colors here because these particular images are in wavelengths that you cannot see with your eye. So we color code them so you can identify them. Color is only relevant for wavelengths that are invisible for our eye. There's a table which tells you how hot each of these images corresponds to, the temperature each picture corresponds to, and then there's another table that shows you which layers each of those pictures corresponds to. And if you think that, well, all this looks different just because of the colors, here's a black and white version, and you can see, yes, there's still a lot of differences that you can see. Some patches are bright in pictures and they're dark in other pictures, the same areas. And this is a wealth of information for us determining how the sun works. As I said, we also use wavelengths we can't see with our eye, such as ultraviolet, infrared, radio, and X-rays. And this particular picture shows you examples of that. On the top, we have X-rays, ultraviolet, and another form of ultraviolet called extreme ultraviolet. The middle row is all visible, and the bottom row is longer wavelengths, infrared, and radio. At this point, you might be asking yourself, well, what about below the photosphere? What about going inward to the sun? We've been talking about layers you can see from the surface of the sun on outward. There's lots of layers inward as well. There we cannot use light to study the solar interior. Light does not get past the photosphere. But we can use sound, and the sound which is trapped inside the sun. The sun is actually filled with sound, but there's only very specific tones that are present. So you can consider the sun to be a huge musical instrument. We can see these sound vibrations in the photosphere, and we use them to study the layers below the surface, and this is called helioseismology. These sound waves, the fact that the sun was filled with sound, were discovered a little over 50 years ago now, when observations were taken of the photosphere, and it was realized that the photosphere was moving up and down periodically, with a period of about 5 minutes. It took about 15 years after that to figure out what was causing that. It had to be some sort of mechanical wave, by which we mean either sound or, like you see on the surface of the ocean. After much modeling and observing, it was finally deduced that these are indeed sound waves. The sound waves are caused by boiling, by the same thing that makes your tea kettle or your water in your saucepan make noise as it boils. I don't mean the whistle of the tea kettle. I mean the sound of it bumping and round. The sun is boiling at its outer edge, and that sound is going everywhere, including back inwards. And there's essentially because the temperature changes as you go inwards, it gets hotter as you go inwards. Basically, you have a mirage is created. A mirage very much like when you're driving down a hot road. You see down the road looks wet. That is because it's very hot near the road and it's reflecting back the light upwards. Same thing happens to sound inside the sun, and the upshot is you end up with only very specific frequencies that survive, and they are indeed trapped inside the sun. They fill the entire sun with a very specific pattern and a very specific set of frequencies or tones. Analogous to a piano. A piano has 88 keys, so you can make 88 different sounds. The sun has 5 million different sounds, which we can see and measure, and by very precisely measuring the tones of the sound, we can infer what the conditions are inside the sun as a function of the depth, for instance. So like we use light to look at the different layers going outward from the sun, we use sound to look at the different layers going inward in much the same way. Certain frequencies travel more deeply into the sun than other frequencies do. And by taking many of these frequencies and combining them, we can actually make images, sort of like holography in a way. And in fact, we do a form of acoustic holograms inside the sun. So now that you know a little bit more about how we learn about the layers of the sun, I think maybe you can appreciate that while most of the pictures we see of the sun looks very simple, it's a nice smooth sort of looking sphere with maybe a few spots on it, but in reality there's much more to it than we can see with just one wavelength. It's when you put in many different wavelengths or many different tones of sound that you can begin to be able to get all the details of why the sun is so fascinating.
As always, if you would like to hear more from us, please feel free to get in touch. You can find us on Twitter at @NatSolarObs. You can get us on Facebook at National Solar Observatory. And we now have an Instagram account at National Solar Observatory on Instagram.